If you programmed just a little bit in Haskell, you probably know what is IO monad. Many Haskellers know about this monad and many can use it, but not everybody knows what it actually is. And for most of the people, IO monad is some kind of a syntax sugar to do side effects in a pure functional programming language. So today I decided to take a closer look at this particular monad and demystify it and actually try to understand what it is. To understand what is IO monad, we need to understand what is pure functional programming. I think to understand what is pure functional programming, we have to look at it in the contrast with procedural programming. What is procedural programming? Generally, procedural programming is programming through composing procedures. You have a procedure, and inside of that procedure, you invoke other procedures sequentially. And those procedures call in other procedures and so on and so forth. They make side effects. So it's a really imperative approach where we say to our computer exactly what to do and when. And in contrast, let's take a look at how generally pure functional programming is happening. Well, pure functional programming is the programming through composition of pure functions. So generally, it will look like that. We have a bunch of pure functions and we just compose them together. And yeah, ideally, pure functional program is just a huge composition, single huge compositions of pure functions. And what is a pure function? Pure function is the function that does not perform any side effects, and on the same set of inputs, it always returns the same set of outputs, no matter how much you call this function, so it's equivalent of mathematical function. And this approach, in contrast with procedural programming, is really declarative, and here lies the problem. Since pure functions don't have any side effects, how can you even write a useful program in such language? Aren't side effects exactly what we write software for? Like, because we want to run a software that performs a side effect and does something useful. This has been a problem in functional programming world for quite some time, and functional programming has invented a lot of different solutions to work around this nature of pure functions. And today we're going to talk about a couple of these solutions. Okay, what is IO monad like syntactically in Haskell? From the Haskell perspective, you can treat it as an indicator of a side effect. So if you want your function, your value to perform some kind of side effect, you mark it with IO, and compiler automatically checks that it does not collide with your pure part, and you don't try to perform side effects whether they shouldn't happen. So you can treat it as a sort of like a really convenient syntax sugar. So let's take a look at some of the examples. For example, you have a value 5, which is integer, but yeah, reality is a little bit more complicated. It's just something that is a number, because there are many kinds of numbers in Haskell, so we're gonna actually work with integer. So yeah, this is an integer. You can actually wrap it into an IO using return, and now it's IO, which contains an integer. So IO is some sort of a container that contains a value, but also performs a side effect. On top of having IO, in Haskell we also have so-called do notation, which is actually the syntax sugar that helps you to write imperative code with side effects in Haskell. Let's take a look at the example. Let's write a classical program which is called what is your name, which basically asks your name. Since this function doesn't take any arguments and doesn't return any arguments, it will perform only side effects. We're gonna mark it with just IO and say that it returns nothing. This is like a void value in Haskell. So then, to start programming in imperative language, we create so-called do block. And inside of do block, we can actually perform like side effects. What we can say, we can put a string saying what is your name, right? On the next line, we can read your name from the standard input. So this is how you read it. This function reads a line from the standard input and binds it to a variable name. And then what you do, you say, hello, that name. Really simple, something slightly complex than hello world. Let's compile this thing and let's try to run it. Excuse me. I guess it killed my Emacs. You see what side effects do to you? Okay, so the program asks, what is my name? I say that my name is... what is my name, by the way? Alexei. And it says, hello, Alexei. You see, even though it's a pure functional programming language where only pure functions without side effects are allowed, suddenly I can program in Python in a really imperative way, just do things as I would do in any other language. But what I/O actually is it just a hack to fit, imperative programming into functional programming, just because functional programming is so poor that it's impossible to write even useful in it? So let's try to find out. So let's actually remove I/O from Haskell and try to think how to implement side effects in a pure functional language where we program with pure functions that by definition don't have side effects. How to do side effects in a language where you're not allowed to have side effects. It sounds like it's a crazy problem. Like, no, you cannot by definition. I just love this comment. You just switch to a good language. Yes, that's exactly what we're gonna do today. Thank you. Let's actually try to look at it from a different perspective. What is a side effect? Side effect is something that modifies world. What if we take world and put it into Haskell? What if we will be able to have a type world which contains the boil state of the world, the boil state of the universe, the state of the elementary particles, everything. And then we could have a function that takes the world and returns another state of the world. And that function is going to be completely pure, even though it performs side effects. Because side effects are relative. For one system, it's a side effect. For a bigger system, it may not be a side effect. So if we were able to capture the entire state of the world and then just slightly modify it, we can create a pure function that takes the state of the world and returns another state of the world. For example, I have a function that prints a string on the console. It takes a string, it takes the current state of the world and returns another state of the world where that particular string is printed on my screen. It's a pure function. It's a really pure function. If you take the same state of the world down to the elementary particles and the same string, no matter how many times you invoke this function, it will always produce the same world. But the problem is that you cannot do that in real world. It's really irrelevant right now. Let's actually think of it like philosophically. Another function that you may have is the function that reads a string from the console. Basically, it takes the state of the world and returns a pair, the input of the user and the world where that user provided that input. We can have these two pure functions. Their implementations are not relevant right now. Even though they are not relevant and they seem to be impossible, we're going to implement them and they're going to work. Trust me. I'm an engineer. But I don't want to show you the implementation. I'm going to reveal the implementation of these functions after the video. Let's create a secret module where I'm going to copy paste this thing and I'm going to implement those functions so they work. But I'm not going to show you. I'm going to show you after the video. Okay, we have implemented these two functions. We're going to import the secret module and we're going to load it up and let's see how they work. To print a string, I have to provide the string hello world and the state of the world. And it printed the string and returned a new state of the world, as you can see. So it's not a magic. I just implemented these functions and they work. See, this is exactly the type of this function. String, world, and world. And we can also read the string from the user, provided the state of the world. We say hello, and it returned the string hello that it read from the input and the world where that string was read. So yeah, we have two functions that are absolutely pure and can perform side effects. So yeah, as you can see, it's absolutely possible to have side effects in pure functional programming language where you can capture the state of the boil world. But how do you write imperative programs with that? Let's re-implement what is your name function, but I'm gonna call it what is your pure name. And this function is obviously takes the state of the world and returns another state of the world. It takes the state of the world where this function didn't ask about our name and returns the state of the world where it asked for our name and said hello that name. So let's try to implement that function. So since it's going to modify the world several times we need to keep track of the state of the world. So initially we take world 1 and we have to return another world. We're going to use aware syntax. First thing I want to do, I want to print a string saying what is your name, providing the first state of the world. By doing that, we get the second state of the world, which we are going to use to read the string. So you see, we take the state of the world where that string is printed, then we invoke this function, which returns the input of the user, and the state of the world where that input was provided. And after that, we go in for the fourth state of the world and print something like hello name, providing the previous state of the world. And as you can see, this is the last state of the world, which we have to return from this function. So you see, if we want to have a pure function that performs side effects, we have to chain several world modifications and keep track of the state of the world. So we can probably also want to format it a little bit so it looks a little bit more nice. And as you can see, we have 3 consequent actions, and it really actually looks like imperative programming, but this function is absolutely pure. It's absolutely pure mathematical function which describes the program that asks for our name. Okay, let's try to compile that and run this function. To run this function, we have to provide the initial state of the world. It asks our name, let's provide our name, and it says hello Alexei and returns the next state of the world, actually the fourth state of the world. This is how you would write an imperative program in a purely functional way where you can capture the state of the world and just pass it around. And let's take a look at a more interesting example. Since world becomes first-class object, we can actually pass it around and maybe copy it. So that means we should be able to write the following code. Let's create a function branch, which takes the state of the world and returns a pair of 2 states of the world where we do the following thing. This function compiles, and what it does, it takes a single state of the world and prints I love you using that world and I hate you using the previous state of the world, and basically splits 2 worlds where the program says I love you and in another world it says I hate you. This actually creates a problem because in real world just doesn't really split. Maybe if you consider like a multiverse theory, maybe it does, and maybe this particular approach can be useful in quantum computing in the far future. Why not? I think it's actually possible, but today, right now, it's actually a problem. We can split worlds and it doesn't match to real world programs. So how can we solve that problem? So our goal is to not allow to use world twice. You can use one state of the world and you're not allowed to use that state of the world again. We have to somehow to prevent users to do that. And there are several ways to do that. Let's take a look at the first one. The first one is called uniqueness typing. Uniqueness typing is actually a very interesting idea where we extend type system and actually ask compiler, please check that the user does not use a particular value of a type more than once. Basically, a compiler can actually check for these situations and just reject such code. And you know what? Languages where that is implemented actually exist. One of such languages is called Clean. It's a very unpopular programming language, but it has a pretty good implementation of uniqueness type. Let's create a separate folder where we're gonna play with Clean and create a file hello ICL. I couldn't find any mod for Clean for Emacs, but I figured out that Haskell mod actually works just fine. So let's try to implement a simple hello world program in Clean. First thing you have to do, you have to declare a module with absolutely the same name as the name of the file. Then you have to import standard environment of the language. And you have to define an entry point. And you know what is the type of the entry of the Clean program? It's a star world to star world. There is an actual language that has a world type. You thought that I made up this type? No, there's actually legit languages that have world type, and it's not like a dummy thing in our case. So this is the entry point of the Clean program, and it takes a world. What I like about Clean, its syntax is really similar to Haskell, so it's not going to be too much for me to explain. First, what we do, we use binding syntax. So Clean allows you to create bindings using a hash sign, something like that. So if you do something like this, it creates a bunch of bindings that you can use later, for example, in condition guards. For example, if A is less than B, then you can do one thing, and otherwise you can do another thing. So you have a section where you define bindings, and you have a section where you have condition guards, which lead to different execution of the function. So in our case, we're gonna do side effects in the bindings to keep track of the state of the world. What we need to do. In Clean, you cannot directly print on the console using world. First thing you have to do, you have to actually extract console from the world using std.io function, which takes the world and returns the next state of the world and the console which you can print to. So you first have to extract the console where you can print. The next thing you do, you write to that console. So yeah, and console actually acts similarly to the world. You print to that console and it returns another state of the console. Everything is pure. If you modify something, yeah, you have to keep track of it. And after working with the console, you have to actually exit it. You have to close it, and you do it like so. So you provide the console that you want to close and the world where you can close it, and returns another state of the world where that console is closed. And in case of an error, it returns like, exit code for you to handle it. Now we can check for errors. If closing console produced an error, we have to abort the execution, saying that cannot close console. Otherwise, we return the next state of the world where we have printed hello world. And now let's try to compile this program. And it compiles. As you can see, it perfectly compiles. It produced a couple of warnings, but it's still compiled, and we can try to run it. And yeah, it printed hello world and some information. I don't know why it generated that information, but here you go. So let's try to use the branching trick in that language. Since you can only print something on the console using the console object, we're not going to use world, but we're rather going to use type file. Console has type file. And what we want to have, we want to actually take one file and return two files. And we're going to try absolutely the same situation. Writes I love you, providing this console, and F writes I hate you, providing absolutely the same console, and we try to split console in the world. And now let's try to compile that code. And you see what happens. It throws a uniqueness error. Demanded attribute cannot be offered by shared object. So if you try to use a unique type twice, and by the way, unique type is indicated with a star, it's a compilation error. The compiler will simply not allow you to do that. So the only way you can write this program is to, instead of returning two files, you have to return one single file, and you just keep track of the consoles. And that's it. And that will work. And it basically, compiler forces you to sequentially execute unique objects. But what's cool is that Clean provides some hack for you to not keep track of, different variable names. For example, you can just rename all of these consoles with absolutely the same name, and it's still going to compile because the next binding sort of shadows out the previous one. So you don't have to remember which word I use. Do I use C1 or C2, C3 or C4? You don't have to think about it. You just basically use the same name, which shadow each other. So it's a little bit easier. And we use absolutely the same situation in Hello World. So this is how this particular problem was solved in Clean programming language. But Haskell decided to go the other way. And one of the ways to solve that problem, apart from uniqueness type, is just to make world inaccessible to the user whatsoever. So how can we make world inaccessible? One way is to introduce something called world transformer. World transformer is going to be a function that transforms the world. So let's try to define such type. We're going to call it world t. It's going to be parameterized with some value, and it's a function that takes the state of the world and returns some value plus another state of the world. So this particular type hides the world from the user. And since the world transformer is actually a function, we can compose them together. The user doesn't have to know about world type at all. What user needs is just world transformers that they can compose together. So let's try to explore this idea a little bit more. So we have functions like print str and read str, which work with the world directly. Let's try to create wrappers that work only with world transformers and don't work with world directly. First, a wrapper is going to be read strt, and surprisingly, if you take a look at the type of read str, it perfectly matches the type of the world transformer. So read str is already compatible with the world transformer. It is the world transformer. It's a world transformer that returns a string. And we can implement it like so. The next thing that we have to implement print strt. This type will take a string and return a world transformer that doesn't return any value and just takes the world and prints that string in a new world. So how are we going to implement that? We're going to take the string, the world, and we're going to return the pair. First element, nothing, because we don't return anything. Print string doesn't really return any value. And then we just use print str as w. And here you go. Let's try to reload this thing, and it compiles. So we just adapted read str and print str to world transformers. So we can now reason in terms of world transformers. But now we need to be able to compose those transformers together. And before we jump into implementation of the composer, we need to understand what is carrying and uncarrying, which are really important concepts in functional programming. So we can understand them by providing some examples in JavaScript. Imagine that you have a function f that takes two values and just sum them up. And how do you invoke this function? You invoke it like so. And this particular thing should return you 30. Makes sense, right? So how do you carry it? Well, you create another function with a single argument. So you make a function of a single argument. Even though you carry a function of two arguments, you create a function of a single argument, which returns another function, which takes the second argument. And inside of that function, you already sum up these two arguments. And you invoke the function like so. So when you invoke it like that, instead of failing, saying that this function accepts two arguments, it actually returns you a function that takes one argument and substitutes the first argument with already provided value. And then to make a full call, you do something like that, and that already returns you 30. So this function is carried. So this is how you carry things in functional languages. Because functions are first-class citizens, you can treat them as values, and you're able to do that. This particular trick is really useful when you want to partially apply a function, basically bind some of the first arguments of the function to some value to make the resulting function shorter, just to put it somewhere, for example, to a map operation. So yeah, it's a pretty common trick. And there is opposite operation, which is called uncarry. Imagine that you have the same function, which is carried. So you have a carried function and you want to uncarry it. So you create an operation, uncarry, which takes that function and returns another function and calls the original function like so. So you see, it basically takes carried function with nested functions and adapts it to uncarried function. And in Haskell, we even have function uncarry. So let's take a look. So yeah, it takes carried function. You see function that takes one argument and returns another function that takes another argument and then the result, and returns uncarried function which only takes two arguments. So this particular function is going to be really useful to implement our world transformer composer. So okay, we need to come up with the name of such world transformer composition. I want to go with the following name. And I'm going to explain why later. So this particular name is going to be really convenient. For those who know Haskell, you understand why I choose this particular name. Okay, so how can we compose two world transformers? So first we take the world transformer that returns type A. And we usually want to do something with that particular type A. So that means as the second argument, we need to take a function that takes type A and returns another transformer T, which returns something else. So you see, we take a first world transformer and we want to do something with A, and we usually want to do something with it. For example, in case of read str, as you can see, we read the name and then we want to do something with it. That's why we need this function, which is able to take something that is returned by the previous world transformer and return you the next world transformer that returns something else. And after that, we return that new world transformer that was returned by the previous function. And that particular operation will help us to compose the chain of world transformers without working with the type world directly. And that's exactly what we're going for. How can we implement this particular operation? Let's actually take the first world transformer and the function that we want to compose it with. So the implementation of this particular operation is not that difficult, but we need to be aware of something that I like to call inter-alias composition. I don't know why I want to call it like that, but I just like the name inter-alias composition, because world T is not a separate type. It is not. It is actually type synonym, which is basically an alias in Haskell world. And that type synonym is a function from world to world. And what that means Haskell treats world T and this function as absolutely the same type. Absolutely the same. It's not gonna even make any like type mismatch error if you try to, use them interchangeably or something. So because of that, if we drop all of the aliases, the world type of this operation is going to look like that. So world T is a function from world to a world, right? So this single thing is actually this function. Then the next is a function from A to world to B world, right? Because we unwrapped the alias. And this one is actually world to B world. So this is the full type of this operation if we drop out all of the aliases. So this is how huge this operation type has. So while implementing that particular operation, we have to be aware of alias and inter-alias composition. And I'm going to show you what I mean. And now look at the type that is returned by first world transformer. Look at this type. And look at the arguments that the function takes. It takes two functions, but function f is uncarried. So you remember the type of the carry, it takes A, B, C and squashes two arguments into a pair, right? So that means if we take f, which has this type, and uncarry it, it will have type A, world, B, world. So if we uncarry f, it will have this type. And notice that this type matches the type that is returned by the previous world transformer. That means we can compose uncarried f with the world transformer. And this is the implementation of this operation. So it actually sounds really difficult to understand and looks like maybe I'm doing some magic here, but it's all about connecting dots together. You cannot compose this function and this function, but if you uncarry it, the first argument of this function becomes compatible with the result of the previous function, and you can magically just compose them and it will work. So now we have an operation that allows us to compose world transformers. Let's try to use it. Let's try to implement something with it. And as usual, we're going to implement our usual hello example. So what is your pure name? But we're going to have another name, T. And since the type of the previous what is your pure name was from world to world, the type of this one is going to be world T, which returns nothing. So how are we going to implement it? First thing we have to do, we have to print string saying what is your name. Now we need to compose with the function that reads the user input. Since this particular function does not return anything, we compose it with a function that just basically ignores the argument. And inside of that function, we read the user's input. And then we compose it with a function that uses that user input and prints hello, that name. I think this is not going to compile. It does compile. Cool. This particular thing compiles. It doesn't use world directly anywhere whatsoever. And that's the beauty of it. We don't work with world. We don't keep track of it. We do nothing. We just compose world transformers and we don't need to know about world at all. So let's try to run this function. What is your pure name T? But if you invoke this function, you still need to provide the initial state of the world because the definition of world transformer requires you because as you can see, world transformer is a function for world to world. But inside of that function, we are not aware of the world at all. And yeah, so it's kind of funny. It actually mixes up pure evaluation and side effects. That's why it's kind of weird, but it still works. It still works. And you know why it does it like that? Because world transformer returns a pairs that contains the value and the side effect. And you see we have side effect inside of the second element of the pair. So yeah. It's kind of funny. And after that, since we don't work with world directly, we can actually basically hide the implementation of world T and the world type completely. And a user may only work with world T. So what can I say? Congratulations. We just reinvented IOMoNAD, because IOMoNAD is exactly that. It's just a world transformer that you can compose with some operator. But what's interesting, what about do notation? Well, you can do that with this particular transformer as well. You just have to prove to Haskell that this world transformer is a monad. And once you've proven to the Haskell that it's a monad, it will automatically let you use do notation as you would do with IO. And monad in Haskell has an operation that looks like this and has the type that looks like this, which might look familiar. So you see it takes monad function from the value inside of monad and another monad and returns that another monad, which actually corresponds to this particular type. So yeah, we have to prove that world T is a monad and that our operation of composition of world transformers is equivalent to monadic operation of bind. So we just need to prove that. But the problem is, in JHC, I couldn't find an easier way to prove that our world T is a monad without writing a lot of boilerplate, unfortunately. And another problem is that it's kind of difficult to implement type class instances for type synonyms. As you can see, world T is a type synonym. And the first thing we need to do, we need to wrap it into a new type. Let's call it a world M for a monad. And it's going to be just a simple wrapper over world T. So yeah, basically new type wraps some type into another type, making them equivalent but different. Type synonym creates alias for the type and Haskell treats them differently, but new type actually creates two separate types. So we need to do that to simplify our work with instances of type classes. So the easiest way to prove that that thing is a functor is to derive it from the functor, because JHC can automatically prove that something is a functor. But I'm pretty sure we have to enable a special extension for that, if I'm not mistaken. So let's quickly do that. Language derive functor. All right, let's reload and see if I didn't make any mistake. Okay, so this compiles. JHC successfully proved that this is a functor. The next step is to prove that this thing is an applicative. So you cannot easily prove that it's an applicative just by deriving from it. You need to implement an instance of applicative. To do that, we need to implement a pure operation that wraps any value into world M. We can do that by wrapping a lambda that takes state of the world and returns a pair of that value plus that state of the world without any modifications. Second, we need to implement an applicative operation that composes two world transformers. The left world transformer contains a function that we need to apply to the value inside of the right world transformer. To do that, we unwrap the left transformer extracting the function, then we unwrap the right transformer extracting the value, and then we just apply the function to the value, wrapping everything back into the world M. Next, we need to prove that world M is a monad and that our composition operation is equivalent to monadic bind operation. The implementation is pretty straightforward. We unwrap world transformer and the function, we apply our composition operation, and we just wrap everything back into world M. Okay, you can't easily do that because we have an incorrect infix precedence. So let's actually try to fix it. What's interesting in Haskell particularly is that you can assign operator precedence for your operators. So we created a custom operator here and we can specify its precedence like so. I don't really remember what this number means. Maybe the higher this thing, the more precedence it has or something like that. I don't really remember, but this particular fix works. So we just proved to GHC that world M is a monad. And after we've done that, GHC gives up and allows us to use do notation with our own IO monad. But that's not enough. Since we introduced another type over world T, our read strt and print strt types became incompatible with world M, which allows us to use do notation. So let's actually make an adapters. Let's create print strm, which takes a string but returns world M instead of world T. And the easiest way to implement it is just to compose world M constructor with world strt. So we basically made a wrapper that works with world M. And for read strm, which should have type world M as string, we just wrap it with world M. Okay, so now we have adapters which work with our new monadic type, and let's try to implement a function that utilizes do notation in our own custom monad. What is your name? Read strm, print strm, hello, ++ name. Okay, so let's try to compile it. I forgot equals. Very sorry about that. And it compiles. So yeah, our monad actually compatible with do notation. Let's try to run it. So you cannot easily run it because first we have to transform it back to world T, and after that apply the initial state of the world. Okay, and now we can work with it. Okay, so as you can see, it works and it even integrates with do notation. So we truly created our own IO monad. And I hope I actually demystified IO monad for you. So IO monad is simply a transformer from one state of the world to another state of the world plus result of the side effect operation. But the trick is world type is practically hidden for you. And what you end up with is composing functions as in any functional programming language. But what's interesting, we implement everything in terms of read str and print str functions, implementation of which we don't really know. And now I want to reveal the implementation of these two functions. Let's take a look at the secret module that I didn't want to show you. This is how this implementation looks like. It uses unsafe perform IO. It takes IO monad and unwraps it. Please never ever use this operation in your code. I beg you. Unsafe perform IO is considered to be a go-to of Haskell, and I only used it here for educational purpose. So we not only implemented our own IO, we implemented our own IO in terms of existing IO.